Okay, we are recording now. Good morning. I hope you guys are able to hear me clearly online. So we don't have too many people that are present today. It's a bit concerning, mainly because it is one of those lectures which is different from the past material that we have seen. So far, we have been talking mainly about computer architecture, right? The last idea that we were talking about was pipelining. We finished 3 lectures on pipelining. Now we are going to start talking about memory organization. And this topic, memory, we're going to use this to transition from computer architecture to operating systems. So memory will give us that connection, that bridge. We have several parts to this topic, memory. In fact, there are 5 parts, memory 1 through memory 5. Let us see if we can complete that in, say, 4 lectures. I'm going to try. So today, in memory 1, we will be talking about the concept of memory hierarchy and the principle of locality. These are the 2 ideas that I want to focus on. And while I do this, I'm going to talk about cache. I'm going to talk about how do you improve the performance of a cache. What is a set associative cache? What is a direct mapped cache? Those other ideas. Now, whenever you think about memory, I hope everybody agrees that they want infinite amounts of very fast but cheap memory, right? So even if you sort of don't worry about the cheap memory, maybe you are very rich, you don't care about the cost, but you will still care about the fast nature of memory and the fact that you want unlimited amounts of it, right? You want a really, really large memory that has to be really, really fast. But now if you think about this a little bit more, you will see that these are 2 contradictory objectives. If you want something to be really fast, you want to search a smaller space to get it, right? So if you want something to be fast, say if I was searching for 1 student in a row of 5 students, it would be much faster than searching for the same student in 100 students, right? So the smaller the memory is, the faster you are going to be able to search for things. But everybody wants big memory and everybody wants fast memory. Contradictory goals. So what are we going to do? We are going to have a hierarchy of memories, and we are going to give the illusion to the user that, yes, they do have unlimited amounts of fast memory by arranging them in several levels. So it's an illusion to the user. Now, as we are building this hierarchy of memories, what is at the very top? When I say at the very top, I'm talking about the closest to the CPU, closest to the processor. The closest to the processor is cache memory. After that, you will have your main memory or dynamic RAM. Cache, the technology that you use to make cache memories is static RAM. Followed by that, farther away from the CPU, you will have main memory. Away from that, you will have your solid state drive. And then you will have your secondary big time storage, your hard disks. But even before that cache, you could include something like a register file. Even smaller space and much closer to the CPU. So that could be your top level. Register file, we know that. We have seen register file while we were talking about MIPS ISA. Now, when you talk about cache, the technology used to make a cache memory is static RAM. And static RAM in computer components and operations, I hope you remember we talked about a static RAM cell. it had 6 transistors, right? Or in general, static RAM cells could come in 2 flavors, 6 to 8 transistors to store 1 bit of information. You guys remember that from Coco? And there was no refresh required here. The only problem with static RAM was what? We had too many transistors in a given amount of die space. So it was not very dense memory, which is why we started talking about dynamic RAM. So if you wanted a lot of memory, then you would have to tightly pack it into a small space. So 6 transistors or 8 transistors are not going to cut it. You're going to need, in dynamic RAM, what did you have? You had 1 transistor, and depending on whether it turns on or off, you were able to charge a capacitor or not, right? So there was just in one DRAM cell, you had 1 transistor and 1 capacitor. If you need a quick refresher about static RAM and dynamic RAM, just go back to your Coco from whenever you took it, look at one of those last lectures on memories. This will be there. And over here, your refresh is required. So that was your main memory built by dynamic RAM. Below that, you can have solid state drive. Solid state drives don't have any moving parts, no moving parts. But the advantage that they have is very fast access times. So if you have a pretty big, decent sized memory in solid state drive, which has a very fast access time, that can help you reduce overall access time. And later on in the lecture today, we will see how we can use a static solid state drive to actually reduce overall memory access time. We'll see that later. And then at the very bottom, you can have a hard disk drive. We are talking about magnetic tapes, right? Your secondary storage, your backups, wherever you have to store large amounts of data. And beyond that, you could have something like a server, where you want to offload all that data to some really high a server which is responsible to hold very large amounts of data, right? So which you can access maybe through a network. So that could be your hierarchy. Closest to the CPU, register file, and all the way down farthest away from the CPU, a hard disk or a server. Now, as you're going down, what is happening to the size of the memory? Can I say it is increasing? Register file, smallest, server, biggest, right? So as you're going down, you are increasing the size of memory. How about the cost? Which one is the cheapest? Which one is the most expensive? Well, the most expensive is going to be at the very top, because now you have 6 or 8 transistors in a small amount of space, as opposed to not that many in the same area. So you are going to be, which is why you don't have a lot of cache. You have a smaller amount of cache typically. So you are very expensive at the top, but as you go down, that cost per bit goes down as you go down the levels. So this is how we are going to arrange things, right, in a memory hierarchy, to give that illusion that we do have unlimited amounts of fast memory. Well, cheap, everybody wants that, but you're not going to be able to get it if you want large amounts of data, large amounts of memory. Now, in order to talk about this hierarchy, memory hierarchy, I would like to use an example from the real world. What is that? Think about searching for books about computer architecture in a library, right? So think about a campus. On a campus, there can be several libraries, and inside each library, you can have several shelves, and inside each shelf, you can have several books. And where are you going to read those books? maybe on a desk, right? So first you are going to have to search. If you are looking for computer architecture, what are you going to do? You are going to search for which library on my campus has computer architecture related books. Then you are going to go to that library, then you're going to search for which shelf, then you're going to go to that shelf and then search for which book, and then maybe bring it to your desk to read it, right? That's how you're going to go down in your hierarchy of libraries for books on a certain topic. Computer architecture is what we are considering here. So say you go to that and you have started to pull out a collection of computer architecture books and you have taken them to your desk from the shelves. Now, let's say that you are looking for a book specifically on the concept of pipelining, and you find that missing. In the books that you have got to your desk, you're looking for pipelining content, it's missing. Where are you going to go and search? You're going to go back to the shelves and going to look for the books, right? And you are most likely going to go where? You're going to go probably to the same shelves, the same space where you were searching for computer architecture book. Meaning, wherever you had computer architecture books, that's where you are most likely going to find it. Next, what are some good chances here? There's many topics you may need can be found on your desk. Once you get all your computer architecture books on your desk, there are very good chances that all the topics or many of the topics that you want to read about, you're going to find immediately on your desk. Something like, if you have got data into your cache, there are very good chances that you will find it in the cache because you have recently got them into your cache from lower levels of memory. And most of the time, you're just using the books on the desk. What are you not doing? You're not going back and forth between the shelves and the desks, right? You're staying there. So you have to rarely go back to the shelves in that case. What is this going to do? This is going to save time compared to having only one book in front of you on your desk and constantly you having to go back to the shelves to take one and return the other, right? So you have a large shelf. You're not getting all the books there. Why? Your desk cannot hold all the books, right? From main memory, you don't get everything into your cache because cache is not big enough to hold everything from the main memory. You bring some things to the cache. And there are very good chances that whatever you need is already there in the cache. So you don't miss in the cache, which is fast, giving you what? Very fast memory access times. What you don't do is, I will get whatever I need from the shelves whenever I need it, right? Like you don't go back and forth between the shelves and your desk all the time. Something like, I will always go to the main memory, the dynamic RAM, to get my item that I'm searching for in memory. You don't do that. So that's sort of a real world example of hierarchy of libraries on a campus that you can sort of relate to the memory technologies. In this case, what is it? Here we are talking about a desk. There we are talking about cache. Shelves are our main memory. One library is our hard disk. Campus of libraries is our server, right? Like that's how we are going down. This slide just shows you some of the aspects of memory that we have already started talking about. So you have your CPU. Closest to the CPU, you have your cache, static RAM. Then you have your main memory over here. And then you have your hard disk over here. And as you can see, the size, smallest at the top, largest at the bottom. Who is fast? Cache is fast. And as you go down, you are getting slow moving parts, hard disks, magnetic tapes. In terms of size, cache is the smallest. Why is it the smallest? Because you want to keep your cost down, right? Cache is expensive, so you want to keep your costs down. So you are going to do, you're going to have a small cache. Your largest memory is going to be your hard disk. the lowest in this level. Cost per bit, highest for the cache, lowest for the hard disk. And as you're going through this, you can start relating. If you have put a computer together, you know that these costs are very realistic. The current technologies that are used to implement each level: static RAM for cache, dynamic RAM for main memory, static RAM and hard disk. Those are your secondary storage devices. Now let's talk about these three aspects: capacity, latency, and bandwidth. CPU generates an address, right? I want to read or write to this particular address. Who generates that address? CPU. Where do you search for it first? You search for it in the cache. Why? Because it's closest to me. It is most likely on the same chip as the CPU, right? It could be on chip. The cache could be on chip. So in terms of wire delay, you have a very, very small wire delay while you are trying to read something or write to something on a cache. If you don't find something in the cache, then you go down one level. And then what you do is you bring that from the lower level to the cache, and then you try to read it, use it. That's what you're going to do. So CPU generates an address. You're going to look at it first in the small memory, small and fast, which could be your register file or your cache based on static RAM technology. If you don't find it here, then you can go for a second option, your backup option, which is to find it in the big or slow memory. So you can think of it like this: whatever your memory has, everything that your memory has is in the lowest level of your memory. But there are some subset of that present in your higher levels. Now, in terms of bandwidth, what has the highest bandwidth? Well, the CPU and the cache, that has the highest bandwidth. Why? Because you are able to access it really, really fast. So the time taken to move data from CPU to the cache is going to be much higher over here. So that's why the bandwidth is high over here. But over here, it's going to be slow. So the bandwidth is not that much. Because why? It is off chip. It is not very, very close to the CPU. So in terms of capacity, register file is going to have the smallest capacity, and the capacity increases towards dynamic RAM. And that is what? This is specifically due to the cost. You don't want to invest everything in the cache. You don't want really, really expensive caches. So you have that small cache, big hard disk. Latency, you have your register, which is lowest latency, right? So that's fast memory access time. And as you go up, the latency goes up as well. So that is essentially what? Due to size, right? You guys are getting the idea here? Register is small, so the time taken for me to access it is going to also be small. So it's the size of the register file that is dictating the latency. The bandwidth on chip is going to be greater than off chip. So something that you have CPU and the cache, if they are on the same chip, then you're going to have a really, really high bandwidth, right? The communication over here can happen at a very, very fast rate. But to have things on chip are going to mean that this reason is due to cost and wire delays. So something that is a little bit farther away from the CPU, the bandwidth, the rate at which CPU can communicate with your main memory, what exactly do you put on cache? Static RAM cells. Static RAM cells that can store a 0 or a 1. So there are instructions. Yeah, there could be instructions or it could be data. But you can organize your cache in several different ways. We will talk about that. Yeah, data, instructions. You can have both together, but typically you have two separate caches, one for instructions, one for data. In fact, think about multi-processor system, multi-cores, right? So suppose you have 4 processors in a computer, processor 1, 2, 3, and 4. Then each processor has its own private cache. So it's associated with CPU. And what are they holding? They are holding either instructions or data that the CPU wants to work on, read or write. Let's go down on this and say, okay, on the data axis. On a data axis, if the data belongs to the fast memory, then you have a low latency axis, fast memory access time. And that goes for cache or static RAM. If the data is not in the fast memory, then I'm going to have to go down one level and search for it over there. That is going to lead to long latency access in the DRAM, dynamic RAM. Now here, if you are going for dynamic RAM, you only go there when you don't find something in the static RAM, right? Like you only go to the main memory if you don't find something in the cache. What that means is the time that you are going to need to access the main memory, you have already, in that calculation, you have already spent some time searching for it in the cache. So you have to add that time to the next level. We'll see some problems over there as well. So while we are doing all of this, while we are dealing with hierarchy of memories to create that illusion for the user, we are going to do what? We are going to exploit patterns in memory access. Memory accesses have patterns, and that is statistically true. Instructions usually follow each other. If you are executing a set of instructions, let's take an example of MIPS architecture, MIPS instructions that you guys have been writing. You tend to do PC plus 4, PC plus 4, PC plus 4, right? So you tend to execute instructions that follow each other. Nearby instructions are being read often, right? Nearby. It's the same thing like the books on the shelves. If you're looking for computer architecture books, there are very good chances that surrounding books are also related to computer architecture, right? So it's a good idea to bring all of those books to your desk. Next, what are some other patterns? Loops require repeated fetching of instructions. For loop, there is one instruction that is continuously getting fetched because you want to execute that. It's in a loop. So where do you want to have that? You better have it in the cache because you are going to need to access that particular memory address again and again. Can you see that? So we are trying to exploit some patterns so that we can reduce our overall memory access time. Next, loop indices are accessed repeatedly. Same example. There's a for loop. There's one particular instruction that is getting executed, but the end of the for loop gets you back to start of the loop, right? So that start of the loop is loop indexes being accessed repeatedly. So it's good to have that in the cache as well. If you have a memory array, then you are most likely accessing it serially. Memory array element 1, element 2, element 3, and so on. So all of these patterns help us identify the principle of locality. And in our real world example, what does that mean? That means that we accessed a very small portion of the library's collection for the computer architecture book, right? We didn't search everywhere. After we found our location, we got all the computer architecture books on our desk, and that's it. We didn't need to do much else. Meaning, if you want to do some memory access, try to get that from your DRAM to cache, and then you're generally good. Only a few times you may have to go back to the main memory. And what I mean by generally good is you will find it in the cache. And if you're finding it in the cache, high bandwidth, very fast access time. Rarely you have to go back. So your memory accesses are faster. These are some real memory reference patterns. This is a site that has real data, which is going to help us understand the principle of locality. On the x-axis over here, we have time. On the y-axis over here, we have memory addresses that have been accessed, which includes read or written. And there is one dot per access that has been shown. And as you can see here, let's try to isolate some chunks of data. This is a chunk of data here. This is a chunk of data here. This is a chunk of data here, right? Now, if you look closely, let us try to, x-axis is time, y-axis is memory address. So you see, if I focused on this particular line here, there is a very good horizontal correlation, which means that if I accessed a particular memory address at time 1, I did the same thing, time 2, at time 3, at time 4, and time 5, and so on, right? I kept repeatedly accessing the same memory address. You guys see that? So that's your horizontal correlation in memory addresses. And this one is horizontal, and the horizontal axis is time. So we are going to call this temporal locality. There's a very high correlation in time in the horizontal direction. What that essentially means is if the CPU is generating memory addresses, then it is likely to generate or read or write to the same address as time goes on. Same address, right? It's the same. Same 32. It is doing that again and again and again. Now, the correlation is not just horizontal, but it is also vertical. You see, there's a high correlation even in the vertical direction, which means that if you are accessing one part, one memory address, then the nearby memory addresses are probably going to also be accessed soon, if not just right now. Yeah? So it's like computer architecture books. Around that, there will be other computer architecture books, right? And you will need that. So what I'm trying to tell you is this. Because of temporal locality and spatial locality, you don't want to bring one item, second item, put it back, third item, put it back, and so on. What you want to do is bring the whole chunk into your cache, because there are very good chances that you will use something that is nearby, or the same thing again and again. You guys see that? So these two, the horizontal and the vertical correlation, you can write that as a temporal locality and spatial locality. They are going to be memory patterns of read and write accesses that are correlated in time as well as in space. So in temporal locality, what that means is if an item is referenced, it will be referenced again very soon. If you read a particular book and you moved away to another, there are very good chances that you will come back to the same book. Next, spatial locality. That is in the vertical direction in our previous chart. If an item is referenced, nearby items will tend to be referenced soon. One book, surrounding that, you will have other computer architecture books. So there are very good chances that you will need them, so you can get them to your desk. So you're talking about small chunks of code and data, which is why libraries put books on the same topic together on the same shelf to increase spatial locality. Questions about the principle of locality, which includes two things, temporal and spatial. So we can take advantage of this. During the execution of instructions, the instruction and the data references are clustering, tend to cluster. And you can see that, cluster 1, cluster 2, cluster 3. Okay. Now let's learn a little bit more about memory hierarchy in terms of its terminology. So you have a CPU over here. Let's draw a CPU right here. It is going to generate an address that needs to be written or read from. So where does that address go? You are going to go to search for it in the upper level memory first, typically the cache or the register file. And if you don't find it here, then you will go look at it in the lower level, right? So suppose we are searching for block X, right? I should actually say item X. If I was searching for item X in my memory, I will first go look at it in the upper level. I found it, right? Item X is in the upper memory. What should I call that? I will call that a hit in the cache. I found it in the cache, so that's a hit in the cache. So what do I do in this case? Well, you found it, so just read the data. That's it, you're done. You found the item that you wanted in the upper level. So that's a hit in the upper level. Data in some block or in the upper level, example block X, that's a hit. What is the hit rate? It's just a ratio. It's the ratio of how many hits that you have divided by all the memory accesses that you are trying to do, right? So it's a ratio of that. Say, for example, 90% of the time. That means that 9 out of 10 memory accesses are resulting in a hit. You are able to find it in the cache. What is the hit time? Well, in this case, you need time to access the upper level. That's it. So it consists of RAM access time plus the time to determine whether it's a hit or a miss. Time to determine whether it's a hit or a miss plus the time for you to get the data out. Right? So the time to access the upper level consists of RAM access time and then the time to determine whether it's a hit or a miss. Now, block X is there, but what if we were searching for item Y? Well, if you were searching for item Y, it is not in the upper level. So what do? You come here, you search for it over here. So you spend time here, right? So you first spend time here, RAM access time, determine whether it's a hit or a miss. If it's a miss, then you will go over here and search for it over here. Then you will have another access time that gets added on to this, right? So, and that would be called as what? You missed in the cache, so that's a miss. Data retrieved from a block in the lower level. This is your lower level here, your main memory, dynamic RAM. Miss rate is going to be simply 1 minus hit rate. And miss penalty is how much time are you losing because of that miss. The time to replace a block in the upper level. Why do you replace a block in the upper level? If I didn't find Y in the upper level, I replaced a block in the upper level from the lower level. I brought Y to the upper level. Why did I do that? I wanted Y. I searched for it over here, didn't find it, searched for it over here, found it, but I just didn't get it from here to here. I got it from here to here first. Why? Locality, right? So it's a principle of locality. If I access something, there are very good chances that I'll access it again. So I'll bring it to the cache because I'm going to probably need it again. So time to replace the block in the upper level plus the time to deliver the block to the processor. Those are going to be your 2 times that go in the as the miss penalty. And you can add to this, right? So for example, here you can have a cache, then you can have a dynamic RAM, then you can have SSD, then you can have hard disk. So you can keep going down in levels. Now let's talk about memory hierarchy in action. Say you have this CPU and it is generating an address that you want to access. And the hit rate in the cache is 96%, which means that 96% of the time, whatever item that you're looking for, you will be able to find it in the cache. And the cache in this example is 1 megabyte static RAM. Where is it going to look first? Well, the processor is going to look for its local copy, its private cache. Like I said, each processor will have its own private cache. Right now, we are not talking about multiple processors. We are only talking about a single processor. So processor is going to look at it over here in its local copy. 96% of the time, it will find it here, but 4% of the time, it is not going to find it there. Right? So the miss rate is going to be 4% in this case. And for that 4% of the time, you will have to go to the main memory. In this case, it is a 1 gig dynamic RAM. You try to find it over there. When we have a cache miss, we look it up in the main memory. And the data is transferred as needed. Now, I want to talk a little bit about how that the data is transferred as needed. This is an item. This is a block. Right? So think of it as this is a word, this is a block of words. You don't bring in the word over here. You don't just bring in, so here, first you wanted to get this, right? This item, this word. You found it in the cache. 96% of the time you find it. So no problem, you got it over there. However, if you wanted some other item which was not there over here, say like this, you missed in the cache, you started looking in the main memory, but you didn't get just this, you got the whole block. Why? You got the whole block over here. Well, you get this over there because of temporal locality. But you get this over there because of temporal locality and spatial locality. Nearby memory items will also have you are going to probably need them as well very soon, right? So you just don't get what you need, you get the surrounding items as well to the upper level. Yeah, you guys have seen that? So 96% of the time, the processor can now get the word from the cache. If not, then you search for, there is a very, very small percentage that we have left for what? For the possibility that we miss in the main memory and we have to go look at it in the hard disk. If we get a miss in the main memory, we have to look up that on the hard disk, whatever is next in the hierarchy. And if the word is here, for example, we fetch the entire block of memory, not just the word. And we just answered why, right? It is to, come on, leverage spatial locality. Getting just one word, one item into your cache, that would be a good idea to satisfy temporal locality, because the same item will be referenced again and again. But now you're getting the entire word. This entire word will be coming to your cache. That is to help with the spatial locality. Now let's do a tree diagram to do some calculations about memory access times. So suppose you're trying to access memory, you're trying to access a word in the memory. There are two chances here. You may hit it in the cache or you may miss it in the cache. And if you hit it in the cache, if you find it in the cache, for hit rate percentage, right, 96% in our previous example, then you only have to include the cache access time for that percentage. 96% of the time, your memory access will be cache access time. However, if you miss there, right, if there is a miss, then you will have to add 2 times. One, the cache access time plus the time to fetch the block from the DRAM. If you miss in the cache, you will have to get it from the DRAM, so you'll have to add that time to fetch from the next lower level to this. So what I want you guys to notice is this. This got added here. And then the new time got in. Now, this is for the dynamic RAM. Again, 2 things can happen. You can hit it in the second level, you can have a hit in the dynamic RAM, or you can miss in the second level, miss in the dynamic RAM. So if you hit in the second level, how much time is it going to take? You are going to have first level cache access time, that plus the time to fetch a block from the second level cache. You see that? So one and then the second level as well. That is for the hit. What about the miss? First level cache, this guy, first time to fetch a block from second level cache, this guy, plus the time to fetch a block from dynamic RAM. You see that? And that is keep on, you're going to keep increasing that. Now let's talk about read and writes. They are different. Writes are not very easy to pick up. So I want you guys to pay very close attention. So this is L1, L2, and DRAM, right? That's cache 1, cache level 1, cache level 2, and then DRAM. That's exactly right. Reads and writes are different. When you're trying to read, you can have a read hit or you can have a read miss. Read hit means what? I was trying to read it in the cache. I was looking for something to read in the cache. I found it in the cache. So that's a read hit. There's no penalty for that. All you have to give up in time is the cache access time in that case. But you could have a read miss. Whatever you want, whatever the CPU wants to read in the cache, it is not in the cache. Why? Cache is smaller. So it will have limited number of items. So what do you do in that case when you have a read miss? Well, you stall the CPU, then you fetch the block from the main memory to deliver it to the cache, and then you restart the CPU. You see that? So when you miss in the cache, go to the next level, bring it to the upper level, restart. So that's what you do in terms of read miss. Now, what about write hit? What does write hit mean? How can you miss in the writing in the cache? Good. Yeah. So suppose you wanted to write where? To a particular word, right? And that word belongs to a particular block. That particular word in that block may be in the cache or may not be in the cache. If it is in the cache and you want to write to it, that's a write hit. Yeah. And all you need to do is you update the cache, the word in a particular block. You will update that. But because you updated it in the cache, you will also have to update it in the lower levels to keep it consistent across all the memories. Right? So you will need to update the memory, entire levels for that particular word. You guys see that? So that's a write hit. How about a write miss? Whatever word you want to write to belongs to a block, but it is not in the cache. So what do? You bring it from the lower levels to the cache, the entire block, then you will write to it, then you will update the memory. You guys see that? So you are going to read the entire block, then write the word into the block in the cache, and then you are going to make sure that it is consistent across all the levels that you have. And there are a lot of other ideas in this. There is cache coherence that you will have to maintain. We'll take a look at those ideas in the coming lectures. Let's see. Everybody okay with read hit, miss, write hit, miss? Yeah. All right. Let's do some calculations here. Simple calculations, really. We have a CPU over here, which is generating memory addresses to access. We have cache followed by a dynamic RAM followed by a hard disk. The time to access a cache is 2 nanoseconds. The time that you need to read or write to a dynamic RAM is 50 nanoseconds. And the same thing is 10 nanoseconds for 10 milliseconds, sorry, 10 milliseconds for the hard disk. 95% of the time, you will find things in the cache. And 98% of the time, you will find it either in the cache or in the dynamic RAM. And then 100% of the time, you'll find it in the every one of those 3 levels. So let's try to see what is the average latency of executing an instruction that involves a memory read. How are you going to do this calculation? We are going to start with the CPU generating an address to read. 95% of the time, it is going to find it in the cache, so 2 nanoseconds. So as far as the cache is concerned, you are going to need this, right? 95% of the time, you are spending 2 nanoseconds to read that particular item, memory item. Notice over here, I'm calling it item, right? I have not put specifics in there, like words and blocks. I'm reserving that for later. I'm just calling it an item right now. Now, if you miss it, 5% of the time you will miss it, right? So if you miss it for this 5%, then you will have to look for it in the dynamic RAM, where access time is 50 nanoseconds. So because of that, search in the next level. %5 of the time, 98% of items can be found in the dynamic RAM where the access time is 50 nanoseconds. Next, if you don't find it in the cache, and if you don't find that memory item that you're trying to read in the dynamic RAM, you will have to go for the hard disk where it is 10 milliseconds. So that would give you, because of this, you would get 5% that you have from here that you missed in cache. 98 went here, 2 remains for this guy. So 2% of that 5%, you will use 10 milliseconds. You will need to spend 10 milliseconds. You add up all those, you are going to get your average latency. Why is this average? Because all these numbers, 95, 2%, 98, all these are average hit rates. Questions here? Hit rate, 95%. Miss rate, 5%. Hit rate in the dynamic RAM. Miss rate in the dynamic RAM. So you got 10 microseconds. If you do all of that, you have got 10 microseconds as the average latency to execute a memory read instruction. Can we improve this? And now what we are going to do is, we are going to try to improve this by adding a solid, we are actually adding a level. You guys see that? We have the same cache, dynamic RAM and hard disk. We are in fact adding a solid state drive such that with the SSD hit rate is 99%. And the read latency for SSD is 80 microseconds. So we are adding something over here, SSD. So that 95% you find it in the cache, 98% you will find it either in the first or the second level, and then you have SSD, 99% of the time you will find it in one of those 3. You are adding a level in the memory hierarchy in this case. Hit rate it's not the compiler's job. It is it would be everybody's job. It could be anybody's job actually. So the programmer also has to contribute to that, because the way the instructions have been written can also contribute to that hit rate. So poor programming techniques can change those, make them very bad as well. Not just that, you can also have that memory organization in a different configuration, like what we have over here. By adding that SSD, we have changed average access times. So let's say because of that SSD, 99% of the time we are able to find it. Let us see how it changes your average latency. The same 95% of the time, 2 nanoseconds in the cache, still there. You missed 5% of the time, but 98% of that 5%, you were able to get it in the dynamic RAM, 50 nanoseconds. You got that number. Then the 5% that you missed in the cache, the 2% that you missed in the dynamic RAM, 99% of that you were able to find it in the SSD. the SSD is giving us this. And then if you don't find it in the cache, don't find it in the dynamic RAM, don't find it in the SSD, then you will have 100% for the hard disk, 10 milliseconds. Add that up, you've got what? 184 nanoseconds for this. It's 50 times faster than your previous number, 10 microseconds. So by adding a memory hierarchy level of SSD over here, just to increase that 1% more, you were able to reduce your memory access times by 50 times. So you can really see the power of memory hierarchies by looking at this particular numerical example. Yeah, both hardware and software. Yeah, an operating system has to do with that as well. Questions about this example here? So this is cache, DRAM, SSD, hard disk. Yes. So you're looking for this, right? 5%. That 5% that you missed, that is going to carry over, right? So this 5% is going to carry over all the time. But after that, after you've missed in the cache, you can find it in the dynamic RAM, or you can miss it in the dynamic RAM and find it SSD. You missed in the cache, missed in the dynamic RAM, missed in the SSD, found it in the hard disk, right? So miss rate is also going to sort of multiply as you go down. Miss rate of level 1, and then next miss rate of level 1, level 2, level so on. And then you will have a hit rate. Miss rate of level 1, miss rate of level 2, hit rate of level 3. Cache and memory. Now we are going to be talking about mapping. Why do we need to talk about mapping? Memory is large, cache is small. So when I'm bringing the memory words or blocks into cache, I need to choose specific parts of my memory to bring to my cache, right? I cannot bring everything to my cache because cache is smaller. So how do you know whether an item is in the cache or not? That's question one. And the other is, how do you find it? So to explain this mapping system, I will draw two diagrams. One is for a cache, a smaller cache, and I have a big memory here. Now, because this guy is big and this is small, whatever your CPU generates, CPU is here. Whatever your CPU is trying to read or write, you try to find it in the cache. If you don't have it here, then you will have to see it in here, in the main memory. But you just don't leave it there. What do? You bring some of it here, right? You bring that over there. The question is, when you try to bring this particular item into the cache, where is it going to map to? Is it going to map to one specific location allowed for it? Or any specific, any location in the cache it can go? Where is it going to go? Say, suppose you have, this is, say, I have this as word 0, right? Where is that word 0 going to go in my cache? Is it going to go here? Is it going to go here? Where is it going to go? A direct mapped cache is the simplest option for that mapping, where it's a many to one mapping from memory to cache. What that means is, this particular word, in fact, there will be many words like that. They will only be allowed to map to one location. Map from here to here, map from here to here, map from here to here. And depending on the size, that might be like many options. It's many to one, right? Many addresses in the memory will map to one cache slot. And the reason is obvious. It is much smaller than the memory. So what you can do for this kind of thing is this. You can, in a very simple terms, you can do this. Bring this guy here, or this guy here, or this guy here, or this guy here. Right? There are 4 sort of groups now. You can bring this, or this, or this, or this. So whatever that group has, many words, will each item will map to only one cache slot. So the mapping is many to one. Many memory addresses will map to only one cache slot. It's a direct mapped cache. So for each item at the lower level, there is exactly only one location in the cache where it might be. Let's take a look at that in terms of an example here. Here, we have a 5-bit direct mapped cache. What does this 5-bit mean? 5-bit means we have 5 bits to talk about any memory address. So in our memory, we have 2 levels. We have cache and we have the main memory, static RAM, dynamic RAM. My cache is much smaller than my memory. My memory is a 5-bit memory address. So 5-bit memory address, which means that what? This is indexed by a 5-bit address, 5-bit address, 5-bit address, and so on up to last one. So how many memory address locations do I have? 32, right? So I've got 32 memory address locations. However, so that's my memory capacity, 32 words, right? So I'm assuming that each of these guys is a word. One word, 32 bits, 4 bytes. So my memory is 32 words because I have a 5-bit address space for my main memory. However, my cache is much smaller. So how many, I'm using 3 bits to index my cache. If I have 3 bits to index my cache, or essentially to identify each cache slot, then I've got the cache capacity of 8 words. You guys see that? So I've got 32 words in my main memory, then I've got 8 words capacity in my cache. So where will this map to? Well, this guy, this guy, where will this map to? Well, maybe this guy can map here. To the first one. How do I know that? Well, look at the last 3 bits. 0, 0, 1. That is 0, 0, 1 is for the next one. Hold on. Let me just move this guy over here because the address is for that. And then go through here and then jump here. So the question is, if you are talking about this particular word, the second word, where does it map to in the cache? There's only one location to that. Where is that? Right here. So if you are trying to read it or write to it, you will want that to be in the cache, and there is only one place it can be in the cache. It is that. And the way we know that it is mapped is by looking at the last 3 digits of the memory address and the 3 bits in the index. 001 there, 001 there. So that's called the cache index bits. And the cache index bits, hold on, is number of mappings in dynamic RAM capacity slash, yes, you got it right. So the number of mappings are 32 divided by 8. There are going to be 4 groups of 8 words that you can map. In other words, 4 things can map to one cache slot. So that was one. What is the other one? 001. Where is 001? Right here. Another one right here. Another one right here. So all of those guys are also mapping to the same location. So if you needed that, you would map it same. Those 4 are mapping to the same cache slot. Many to one in this case is what? 4 to 1. 4 memory addresses are being mapped to one cache slot. And that number 4 we are getting because of 2 raised to 5 divided by 2 raised to 3. 4 memory addresses map to each cache slot. 2 raised to 5, what is that? That's your memory address space. 2 raised to 3, it is your cache capacity. 32 words and 8 words respectively. You can see that? So direct map cache, many to one. Many memory addresses are being mapped to a single cache slot. Now, if you look at the memory address, what does it have? It has 5 bits. You know what the last three bits are going to be. The last 3 bits are the cache index, right? Essentially identifying which cache slot. What about the first 2? The first 2 bits are actually called tag bits. They are going to be 00 for the first 8 words, right? So for the first 8 words, 3, 4, 5, 6, 7, 8. For the first 8 words, you are going to have tag bits of 00. That is how you differentiate between which group of words are you currently bringing in to the cache or currently in the cache, right? So those are the first 8, next 8, next 8, and then next 8, right? There are going to be 4 groups of 8 words. So at any given time, you can either have this group in here, or you can have the next group, or you can have the next group, or you can have the next group in the cache. And the way you know which one is by looking at the tag bits, 00, 01, 10, 11, right? 0th group, first group, second group, third group, 4 groups. You guys seeing that? Easy peasy? All right. Now let's take a look at how do you find cache index. For any given memory address, suppose the CPU generates a memory address, and you want to know to which address, to which cache slot is this particular memory address mapped, right? So the memory address in our example is 5 bits. And let us take an example of 17 here, right? So 1, 0, 0, 1, 3 zeros and a 1. That's 17, right? That is the memory address. When you do a modulo 8, so essentially you are dividing by 8 and looking at the remainder. What is the remainder there? 17 modulo 8 will give you a remainder of 1. So the cache index for any memory address can be identified by doing memory address modulo the number of words in a cache. In our example, memory address was a 17. Number of words in our cache was 8. So the cache index is, well, we know it's the last 3 bits, but how do you look at it in terms of a numerical computation? It's just 17 modulo 8, look at the remainder. Over here, so far, we have only been talking about words of memory. But in reality, you don't talk about words of memory. You talk about blocks of words, right? So you just don't have one word in a block. So far in our discussion, that's where we are. You just have one word in a block. A wider memory, a better memory, a memory with lower miss rate is one where you have many words in a block. So you will have to talk about blocks of words. Block is what? It's a collection of words. Oh, wait. Block equals collection of words. Two words per block, 4 words per block, 16 words per block. All right, so this diagram shows you essentially the same things that we have talked about, right? You see, many to one. The blue guys are mapping all to this one cache slot. Similarly, you can look at some other memory cache slot. Suppose you look at this particular cache slot with a cache index of 101. What memory addresses are mapping to that particular cache slot? Ending with 101, this guy. Ending with 101, this guy, this guy, this guy. The tag bits are what? 00 here, 01 here, 10 here, 11 here. So the lower 3 bits of the memory address are specifying the cache location or the cache index. And then the first 2 are identifying which group are you referencing, the tag bits. For each memory address, there is a unique cache slot. When I say unique cache slot, do you guys feel that this is a bit restrictive? Whenever you're trying to bring things from dynamic RAM to cache, you only have one cache slot available for a memory address. It's a very restrictive, right? You're constraining that. It would have been better if things were flexible. If I wanted to bring something from main memory to my cache, suppose a block of words, it would have been ideal if we had 2 options for it. 2 cache slots where I can go, this or this. Maybe this particular one is occupied by something that is severe, right? Something critical, and I don't want to interrupt that. I could go here, right? So that would be more than one cache slot for each memory address. That is called a set associative mapping. This is direct mapped. Direct mapped, you can only have one option in the cache slot. Any memory address can only go in one specific cache slot. All right, let's see. Many memory addresses map to a single cache slot, 4 in our example. We did that calculation, 2 raised to 5 divided by 2 raised to 3 to find that. We just did that over here, right? So we have taken a look at that. And then this is going to be true for the addresses separated by 8s. Group 1, group 2, group 3, group 4. Next. So any word address, you see, this is a word address. Word address means what? Where is it coming from? Its CPU is generating it. It wants to read or write to it. It will do this for 5 bits. Why 5 bits? Because it's a 5-bit memory address space. The last 3 bits are your cache index, 101, essentially identifying which cache slot can any memory address go into or be mapped. Then the first 2 are your tag bits. So you've got tag bits over here, then you have got 3 cache index bits over there. Tag followed by your cache, that makes up your 5 bits for the memory address. The first 2 are identifying which group of 8, and the last 3 are identifying which cache slot you have reserved for any memory address. Questions here? So the tags are distinguishing between which group, right? Questions? Is this kind of heavy or simple, or what's going on? Things are okay? Yeah, all right. Now let's try to increase the size. From a 5-bit direct map cache, we have gone on to 32-bit direct map cache. And we have added some more detail here. We have the tag bits, as we had earlier. The tag bits do what? They help distinguish which group. Then we also have cache index, essentially to identify which cache slot. And then you have a byte offset. Why byte offset? Because with the tag and with the cache index, what can you do? You can do addressing for the word. But what if you want to do a byte addressable memory? Like in MIPS. In MIPS, we had a byte addressable architecture. So when you have byte addressable, you see this one was word, right? So the 5 bits were being used to identify 4 bytes, one word. But what if you wanted the address to be byte addressable? So right now what you're using is a 32-bit byte address. So if I give you 32 bits, you should tell me the byte that is available at that 32-bit address, right? It's a byte addressable. With the tag and with the cache, what do you get? You get a word. But within that word, how many bytes are there? There are 4. One word, 4 bytes. Need 2 bytes, 2 bits. Need 2 bits to specify byte offset. So that's why you have your, all the way to the right, you have 2 bits to help you pick out which particular byte in that word you want to address. 00, 01, 0, 10, 11, right? So that byte offset is just helping you identify which byte in that word that you picked. The word you picked was using tag and the cache, just as we did before. You guys are okay with the byte offset? Byte offset is going to apply for what? It is going to apply for byte addressable memory. If the memory was not byte addressable, if it was word addressable, then you would not need this byte offset. You guys see that? Next, we have 20-bit tag, and then we have a 10-bit cache index. If you have 10 bits in the cache index, how many cache slots do you have? Cache slots equals how much? When you had 3 bits for the cache index, you had 8 cache slots. You have 10 bits in the cache index, you have how many slots? 1024, 2 raised to 10. Where is that? Cache index 0, cache index 1, cache index 2, cache index 3, so on up to cache index 1023. In total, there are 1024 cache slots. So this is the view of a cache right now. So the cache index is specifying which cache line are you trying to read or write to. Next, so you've got 2 bits over here, then you have got 10 bits over here, right? It was a 32-bit byte address. So how many bits are you left with? Well, 32 minus 10 plus 2. So you've got 20. 20 are your what? 20 are your tag bits, right? So 20 tag bits. What does that mean? When you had 2 tag bits earlier, you had 4 groups
of 8 words. Now you have 20 tag bits. So what do you have? You have 2 raised to 20 groups of 2 raised to 10 words. Can you see that? Because even the words, the cache index has gone up. So in your cache, what do you have? You have, let me write over here. Cache has 2 raised to 20 groups of 2 raised to 10 words. You see that? At any given time, how many words can be in the cache? 2 raised to 10, right? At any given time. And like that, they are 2 raised to 20. Okay. Now, let's try to answer this. Your CPU has generated a byte address. How many bits is that byte address? 32-bit, right? So the CPU has said, I want to read this particular 32-bit address. What are you going to do with it? You are going to check it in the cache. You may find it, you may not find it. How do you know? This is what you do. You look at a comparator, and the comparator has 2 inputs. There is a tag bits, the 20 most significant bits in your 32-bit address is an input to that comparator. The other input to that comparator is the tag field inside the cache. If both those match, then the comparator outputs a 1. So you are essentially checking the tag bits in your memory address that you generated, the CPU generated, to the tag field in that cache, right? You're mapping them, matching them. If that is a 1 and the valid bit in that particular cache line is a 1, then you have a hit in the cache, meaning whatever you are looking for, you found it. Each particular data word is going to have a specific tag. You guys agree with that? It is going to have its own tag, right? Because we are going to need to identify which group do you belong to. There are 2 raised to 20 options. So which group do you belong to? I need to know that. So I'm going to have a check for that tag field. Here is my 32-bit data. There's another bit in there, which is called the valid bit. Valid bit essentially indicates in the cache that there is a valid entry in that particular cache line. So whenever you're trying to read a cache, you try to do 2 things. One, the tag bits in your memory address have to match the tag field in the cache, and the valid bit, the corresponding valid bit in that same cache line has to be a 1. If both those things are true, then the data at that particular cache line is the data that you were trying to read. That goes back to the processor. You guys see how this is going to work? Valid bit, tag bits, and your data. Valid bit, what is that being used for? Do you have a valid entry, data entry in that cache line or not? Tag bits. Which group of 2 raised to 20 are you looking for? Whatever you have generated, it has to match over here. If it doesn't match, then that particular cache line corresponds to a different mapping. Next, the data field is just the 32-bit data that is available over there. So far, how many words are there in my block? So if you look at this, right, how many words have I talked about in a block? Block is what? A collection of words. We wrote that over here. So each cache line has how many words? Words per block. How many words are here? How many words per block? Just one. Right? I only have one 32-bit data at any given cache line. So whenever I'm doing this swapping and mapping, I'm only doing that for 32 bits. My index for one cache index, I only have 32-bit data, which is one word. So right now what I have is one word per block. What would the memory look like if you had more? It would look something like this. It would just keep padding on to the right. Let me clear this page off. It would just keep padding on. 1, 2, 3, it just keeps padding on. Then you have more words in one particular block. We'll talk about that next. So you have one word per block in this particular example. So you have word 0, word 1, word 2, word 3, and so on. And then each of them is a block. What is the cache size? How do I find out cache size? The size for my cache. I've got 32 bits at each cache line. I've got 2 raised to 10 cache lines. So what is my cache size? All right. This would be in bits, right? Yeah. What can I say next about this? This is what? Okay. 2 raised to 10 is kilo. 2 raised to 15. What is 32? 32 bits is how many bytes? 32 bits is how many bytes? 32 bits and how many bytes? Equals blank bytes. Almag has got it. 4, right? So 32 bits, you have got 4 bytes. The 2 raised to 10 gave you K. Is 4 KB, 4 kilobyte hash size. You guys agree with this? Thirty-two bits or 4 bytes, right? 4 bytes times 10 to the 10, 10 to the 2 to the 10. 2 to the 10 is kilo. 4 bytes is 4 bytes. Multiply them, you got 4 kilobytes as your cache size. Byte equals 8 bits. Yes. One byte equals 8 bits. Yes. Let's see. Questions about this slide. What kind of memory are we talking about? We are talking about a 32-bit byte addressable direct mapped cache. Because it is byte addressable, we need the byte offset to specify which byte in a word. We get that word by providing the tag bits and the cache index. The tag bits are going to identify which group of 2 raised to 10 words are we talking about. The cache index is going to pick out which cache line are you referencing. There are 2 raised to 10 cache lines here. And the way you read it, any memory address, any 32-bit byte address that the CPU generates, the way you look at it in the cache is you check for the valid bit, you check for the matching tag, and then if they are both satisfied, so that means that you will have to design a comparator over here. You will have an AND gate over here. The comparator has to say the tag bits match. The AND gate has to say the tags would match and the valid bit was 1. In that case, the data, whatever is the data for that cache line, is the data that you were interested in, the 32-bit data. Why is the tag bit 20? Well, 32-bit byte address, 10 bits for cache. So what is the limitation? How do you work backwards? You have a particular cache size, right? For a given cache size, then you can find out how many cache index bits you need. You exhaust the cache index bits, you exhaust the 2 bits for the byte offset, and whatever your remaining you have, that needs to be for the tag bits. Tag is most significant, and all the way down byte offset is your least significant over here. Now, I said you can have more words per block. Right now, we had only 1 word per block. If we wanted to build a wider memory, right? So we wanted something like here and here and here. We wanted more data options. So we wanted to grow this horizontally, the entire thing. We would need to go for a 32-bit direct mapped cache with many words per block. But when you have many words per block, and you want to still be byte addressable, then you not only need to find out byte offset to pick out the byte in the word, but you also need what? Block offset to pick out the word in the block. See that? That is shown over here. This is a 32-bit direct mapped cache, but it doesn't have 1 word per block, it has 16 words per block. Where are those 16? You see, I've grown this horizontally. This is word 0, word 1, word 2, so on up to word 15. There are 16 words at each block. Block 0, block 1, and so on. Where am I ending? Block, well, I'm given 256 here, so 255. Right? There are 256 entries over here. How do I know it is 256 entries? Well, maybe I was given the cache size. So what would be the cache size in this case? Let's just calculate that. Get that out of the way. Cache size. So I'm talking about all of this, right? What would be the cache size here? There are 256 blocks. Rows in this, so 256 blocks. And at each block, you have 16 words. And each word is 4 bytes. Is that okay? So that would be your cache size. What is that going to equal? 256 is 2 raised to 8. 16 is 2 raised to 4. 4 is 2 raised to 2. So when you add all of them up, what do you get? 16 KB. So we had a 16 kilobyte cache, and we had 16 words per block, which means we got 256 blocks, right? So block 0 all the way down to block 255. So the addition is what? The addition is of this block offset. Why do we need that block offset? And there are 4 bits for this. Why do we need this? Well, we are going to need 4 bits to identify one out of the 16 choices that you have. 16 words per block. So with the tag and with the cache, what do you get? With the tag bits and the cache bits, you will identify one cache line, right? One cache line. Then from that cache line, you need to pick out the specific word. You need 4 bits for that. From that, you need to pick out the specific byte. You need 2 bytes for that. So I hope you guys agree that this will always be 2, right? 2 bits. You guys okay with that? Yeah? All right, so let's move on. Byte offset is 2. Why? I need 2 bits to pick out 1 byte out of a word because it has 4 bytes. Block offset is 4 to pick 1 out of the, so this is related to this, right? 1 word out of the 16 words. I need 4 bits to do that. The cache index is 8 bits. So can you guys tell me how many cache lines are we going to have? 256, right? 2 raised to 8 is 256. Where do you see them? Right here. 1, 2, 3, 256 lines. So the cache lines are directly related to the number of blocks. So if your cache index is 8, the number of cache lines is 256, and the number of blocks that you have is 256 as well. So if you exhaust out of the 32 bits, if you exhaust 8 here, 4 here, and 2 here, how many are you left with? You are left with 18. 18 will be for the tag. What does that mean? There are 2 raised to 18 group of such 256 cache lines. And then again, there is a valid bit as well in the cache. So let's try to see when a CPU generates a 32-bit byte address in this wider memory, where we are making it wide by having more blocks, more words in one particular block. Right? We have made it, we have expanded it horizontally, not vertically. Well, we have actually reduced it vertically. Earlier we had 1024. There the cache size was 4 kilobits. Over here, kilobytes. Here our cache size has increased by 4 times. So it's a different cache size altogether. Valid bit here, tag, and then your data. So how are you going to find whether it's a hit or a miss? And then how are you going to select that particular byte addressable data? So let's see. For a hit, a few things have to happen. The valid bit at that particular cache line has to be a 1, and the tag entry has to match with the tag index, the tag bits in the memory address. They all have the same tag, by the way. All of these guys have the same tag. What that means is, whenever you are bringing that group, you are bringing the entire block from main memory into the cache. You're not bringing one word. You're bringing the entire group of words, a block, into the cache. So all of those have the same tag bits, the 18 of them. So you try to look at whether there is a matching tag and the valid bit is 1. If both those conditions satisfy, then you have a hit in the cache for that particular 32-bit address. But how are you going to get the data at that address? Well, it could be, I know that it belongs to this, but it could be any one of the 16, right? So if it could be any one of the 16, I can put all of those 32 bits into a mux and select one out of how many options? How many options do I have here? 16 options, exactly. So I need a 16 to 1 mux in this case, right? 16 to 1 mux. How many select lines? How many select lines for a 16 to 1 mux? 4. Where are the 4 coming from? Block offset. So the block offset was essentially used to pick one word in that particular cache line, in that particular block. Did you have a hit or not? If you had the hit, this is what you read out of it by going through that 16 to 1 mux. Questions here? So the configuration of the memory is also important, right? This is what? 32-bit direct mapped cache with 16 words per block. And the address, the 32-bit byte address, is going to always going to be in that specific format: tag, cache, block, byte. Okay. Now let's try to see how this works. So you can have either a hit or a miss in the cache, or you can have while you are reading, or you can have a hit or a miss in the cache when you are writing. So for example, if you have a read hit, what does that mean? That means that you found things in the cache. So you just read the data from the cache in that case. When you have a read miss, what does that mean? Whatever you wanted to read in the cache, it was not there, so you had to fetch it from the dynamic RAM. So fetch the block. You see, it's the block, not the word, it's the entire block. Fetch the block from the dynamic RAM into the cache and then read the cache. That's how reading would work. Writing, very different. When you have to write to the cache and you hit in the cache, then that means that whatever block, whatever word you wanted to write to, it was already being mapped in the cache. It was there in the cache. So you found it. So you just write to the cache. However, you cannot stop there because you have to update the lower levels as well. So you will have to update the entire block of that dynamic RAM. You update not just one word, you entire block in the dynamic RAM. You update. Group of words. Next, write miss. Whatever you wanted to write to a cache line, you did not have it in the cache. So you had to fetch it. So fetch the block into the cache first, then write the word into the cache, then you update the memory. Because you have to be consistent between the levels. What is the best block size? We looked at, the first example was 1 word per block. Then we said 16 words per block. Did we benefit from that? Well, let's try to look at some examples. Statistically, you have 2 programs over here. One is a compiler, one is a SPICE program, your circuit simulation software. Both programs, for both programs, 4 things have been tested. Block size 1, sorry, in words, right? So this is 1 word per block, 4 words per block, 1 word per block, 4 words per block. And as you are increasing the number of words per block, you are able to find things easily in the cache. So what will happen is, for both the instruction and the data, and then you have the combined miss rate over here, the miss rate in the cache goes down. Why? Because you have built up a wider memory. For the same block, you have given it more words. Why does it go down? Why does the miss rate goes down with more blocks, more words per block? Good. Locality. Exactly. We are leveraging spatial locality, right? So as well as temporal locality, but mainly spatial locality is the main reason why it's able to go down. Because if you tend to use this particular word, reference this particular memory item, then the nearby items, the nearby words in that block will tend to be used as well, right? So you're bringing the entire block. So you got that advantage, right? So because of spatial locality, For any program, see 5 to 2, and then 1.2 to 0.4, the miss rate has gone down, which is good news, by the way, right? Missing less is good, right? So as you are increasing the number of words per block, your miss rate is going down. That's one way to improve your cache performance. Larger blocks means lower miss rate. But there's a problem. You see, these are different cache sizes. Cache size 1 KB, 8 KB, 16 KB. These are all different cache sizes. So there is one plot for 1 KB, then there's another one for 8 KB, then there's another one for 16 KB, and so on. In general, as you increase the size of the cache, the overall miss rate goes down. You guys agree with that? The bigger the cache, the smaller the miss rate. Why is that? Well, bigger cache, right? Bigger memory. So you're more likely going to find things over there. Why don't you go for infinite cache in that case? Cost, right? So cost is the limitation why you come down, and also to keep your access times realistic. But as you are increasing the cache size, your miss rate will go down. So that's one trend I want you guys to observe. The other trend is specifically with the block size in words. Here, the x-axis is block size in bytes. But we know 4 bytes is 1 word, right? So this is 1 word, 4 words, and so on. So when you have 1 word per block, let's suppose we are talking about this 1 kilobyte cache. Then your miss rate is close to 37, 38% when you have 1 word per block. When you go up to 4, it has come down. Reason, spatial locality. You went up to 64 bytes, a factor of 4 here, which means 16 words. When you went to 16 words, because of more spatial locality, it has come down. However, if you abuse it, if you keep on going, you actually increase the miss rate. Why is that now? In terms of memory, you have the same total number of words, right? One way to organize it would be word, like that, vertically. But by having more words per block, you were able to make a wider memory. But if you have too wide of a memory, then the penalty is too much, right? There's too much competition for that one cache line. So if you go wrong, then you have to throw out the entire block of words and bring in the new one, right? Even if you go wrong by 1. So there is only so much you can use with the locality. If you go too much, then the penalty of having a bigger block size is going to hurt you. Can you see that? There is too much competition for each cache line in that case when you have so many blocks per, so many words per block. So this can work only to a point. In this case, about 16 words per block is good. Beyond that, it will increase. So best block size should be chosen for a specific program, by observing that sort of trend. Next, how do you improve cache performance? Well, improving cache performance is reducing the miss rate and reducing the miss penalty. How can you reduce the miss rate? Well, one way to do that is increase the block size, but to a limit. To a point, you can do that. We just saw how do you make the block usage more efficient. By having more efficient use of the blocks, then you can organize your data such that your locality can be really leveraged. So there are some ideas over there. Make block usage more efficient to reduce your miss rate, right? So reducing miss rate, you have these 2 ideas. Making the miss penalty go down, meaning if you miss, the time that you spend for the penalty should be less. That you can do by using faster memory, or you can have multi-level caching. Even the caches are in levels, level 1 cache, level 2 cache, level 3 cache, and then you go to the dynamic RAM. So if you have that multi-level caching, then you are reducing the miss penalty, because all the caches are going to be at a very high bandwidth closer to your CPU. Next, let us look at clear page. A flexible way to map cache. Earlier we said in the direct mapped cache, it was many to one mapping, right? Many memory addresses were mapped to exactly one cache slot. But that is very limiting. Instead, if we had the option of mapping a memory address, any memory address, to maybe 2 options, or 4 options, or 8 options, then it would be a flexible cache. So a few things that we can do here. This first diagram that I'm showing here is a direct mapped cache. A direct mapped cache, the one that we have seen before, is also called one-way set associative. So the association is only with in one way, meaning many to one, right? So this is where a memory address can go, many to only one, many to one, right? So many memory addresses will go to only one cache slot. That is direct map cache, also called as one-way set associative. How does the cache look like when you do that? Well, you have blocks vertically laid out. Each block will have a tag field, and they will have the data, right? And each block, you can have sort of multiple words per block. We saw 2 options, right? One was with 1 word per block, then we saw 16 words per block. Both of those were direct map cache. One was just 1 word per block, then we sort of padded more here, right? But the thing to note over there was each cache line, each block, it had a specific, the same tag bits for that particular block. That is direct mapped. Only one option, only one cache slot for any memory address. Let's talk about fully associative. That's the one that is on the bottom here. 8-way set associative. How many words do I have, or how many blocks do I have? I have eight blocks over here, right? So instead of arranging them this way, I have arranged them this way. Tag data, tag data, tag data, tag data, and so on. 8 of them. There's still 8 blocks, but I have arranged them horizontally. But as far as the options, the mapping is concerned, my memory addresses can be mapped here, or here, or here, or here, or here, or here, any one of the 8. So it is what? Any to 8. I have 8 options here, very, very flexible, right? What is the problem here? So direct map cache was one extreme. Any memory address could go only in one, exactly in one cache slot. Only one seat has been made available for that memory address. Over here, all of the fully associative, it is all of the seats are available. You can go anywhere if you want. Any memory address can go anywhere. What is the problem with fully associative? What was it? There's no locality. Well, locality would be dependent on like the number of words per block, right? So this could be block, this could be block. So this data, that data field could be 16 words per block as well. But now you have, in other words, here you have tag for each data, tag for each data, tag for each data. Over there, you had tag for data, right? So it was, you were searching for things in parallel, right? Now you are going to have, whenever you are trying to search, what are you going to search for? Now you have to search in fully associative. When you go searching, it is no longer going to be in one location, right? You are going to have to search for all the cache slots now. So the access time is going to be huge when you go for fully associative cache like this. In fully associative, right now it's 8-way set associative because there are 8 sets, but it is 8 sets because we started off with just 8 blocks. So it just appears as 8-way is fully associative. The problem with that is the time that you spent in doing that comparator, like because you are going to have to do a comparator to match the tag bits. Now so that's direct map cache and fully associative, right? Those are the two extremes. But the middle two options are here. This is two-way set associative. Two-way set associative essentially means every memory address has 2 slots it can go. It can go here or it can go here. The next one, it can go here, it can go here, or here, or here, or here, or here. 2 cache slots for each memory address. That's called a two-way set associative. So in this case, what you do is this. The way you build the set is block 0 and block 1. Right? Block 0, block 1. Then block 2, 3, 4, 5, 6, 7. So you're essentially grouping them. Once you group them, you're essentially allowing 2 slots for each memory address to come into. And then when you start checking, you have to check here or here. Right? Now you have to check 2 places to match the tag. Earlier you were checking only one, fast. Now you have to match the tag here and here. Slightly slower, but flexibility is there. 2 slots open, 2 slots possible. Or you can go for 4-way set associative, where any memory location can come in one of the 4 cache slots. But now, as you are increasing the 2-way, 4-way, n-way, as you are increasing how many way set associative, you are essentially increasing the time that you spend in matching the tag field, right? So that is going to be the problem, why you don't go for a really, really, really flexible cache. You have to find a midway, right? 4-way set associative is sort of a really good option there. Questions here about like what is set associative mapping in a cache? You're essentially having more cache slots available for each memory address. With direct mapped, there was only one seat available so that they can sit. Now you have said, okay, you have 2 options to go, 4 options to go, 8 options to go. But with that, the problem is with the matching of the tag bits. All right, so that discussion is captured into this. Next, so the first thing is here, reduce the cache misses by using the flexible placement of blocks. So you've got the tag here, you've got the tag here, but because you have made the things flexible, you are going to reduce your cache misses. In the direct map cache, how do you find the position of a memory block in cache? Earlier, we had 1 word per block, and when we had 1 word per block, we found cache index by doing memory address modulo the number of words in a cache, right? Number of words in cache. We can take that same, here, let me just refer to that over here. Where is that formula that we talked about? Right here. You find the cache index by doing memory address modulo the number of words in cache. We are going to take that same formula and apply it to blocks. And when you do that, you end up with this. Block number modulo, instead of block number modulo number of blocks in the cache. That is going to give you your position in the memory block in the cache. Next, in a set associative cache, block number modulo number of sets in the cache will tell you the position in the block, and all the tag of all elements must be searched, right? So that is what is your time consuming part, all the tags have to be searched because now you have more options. What is the total size of the cache in blocks? Well, you can take the number of sets, multiply it with the associativity, right? So, for example, 4 sets, two-way set associative. 4 times 2, 8. What is this? One-way set associative, but they are 8 sets, right? So 8 times 1 gives you same 8. So you can have all of these options that we wrote. 8 sets multiplied by one-way set associative will give you 8 blocks in cache. But there were always 8 in our example. 8 blocks, 8 blocks, 8, 8, 8, 8. We just changed the associativity. Two-way set associative, four-way set associative, 8-way set associative. In each of them, we had 8 sets for direct map cache, 4 sets for two-way cache, 2 sets for the four-way set associative, and 1 set for fully associative. In our case, because we were only talking about 8 blocks, 8-way became fully associative. Oh, let's clear page. All right. So how does the implementation look like for a 4-way set associative cache? There is no block offset over here, right? So there is tag, there is cache index, and there is byte offset. So you're trying to pick out a byte offset. So you're trying to pick out a byte. You're not interested in finding the word in a block. So the number of blocks in a particular word have been assumed to be just 1, right? You guys see that? So only one, only one, only one, only one, right? As opposed to having a second one here. There is only one word, word 0. There's no word 1 here, right? So this type of memory, this type of cache has 1 word per block. It is 4-way set associative, which means that any memory address could go in 4 places, 1, 2, 3, or 4. Right? Four options you have. Then you have the cache index to identify which cache line are you talking about. And then you have the tag index to match the tag field from here or here or here or here. You could have 4 different, right? So you could have this particular group there, and then in the next set you could have another group there, and in the next set you could have another group there. So you can have 4 different tags for that same cache index. One could go here or here or here or here. So how is this different from the one that we saw earlier? Now you look at this, and I want you to compare this with this. Something like this. Where is that? I can see it right here. What is the difference between that guy and this guy? So you see over here, number of words per block are 16. Over there, number of words per block was 1. Over here, for each cache line, you only have 1 tag field, right? So all the 16 words that you have in a block have the same tag index, the tag bits, right? Same tag bits for all of them. But in the 4-way set associative, you have 4 things that could go. They can have their own tag. They can belong to those 4 different groups. You see that? So you have those 22. How do you get this 22? Well, you need this to be 2. Then cache index is 8, which means that there are 256 cache lines, right? So 0 right here, all the way down, 255 right here. So the byte offset is used to pick out the byte in a word. Then you have the cache index to identify which cache line. And then you have the remaining. This is a 32-bit byte address. If you exhaust 10 over here, then you are left with 22 tag bits. Those 22 tag bits, you are going to need to match or compare the 22 bits in the tag field for the address generated by the CPU with the 4 tag fields for that specific cache line, right? So whenever you have this cache, the cache index is going to help you determine what? Which cache line. Then the tag field is going to need to match. So you try to take this tag field, 22 bits, and go into comparator 1, comparator 2, comparator 3, comparator 4. Those 4 comparators will also have inputs from the tag fields for each cache line. One of them will match, right? Only one of them will match. If one of them matches and the valid bit at that particular cache line is 1, then we know it's a hit, right? So this will tell us if it's a hit or not. Or this could tell us whether it's a hit or not. Or this could tell us whether it's a hit or not. This is an OR gate, right? So one of those 4 could be a 1, and you know it's a hit. Too simple, bit complicated. Where are we? You guys are seeing this 4-way set associative? Tag bits are different for each cache line, different from what we had earlier. Earlier, we were just expanding the memory horizontally. Our tag field was the same. We didn't have multiple tags for each block. We had the same tag for each block. Now, for each block, in this case, we have only one word per block. But you could have more words per block in a different cache configuration. Good. Yeah. Right. So it's now able to hold data from 4 different groups there at each line, right? At each cache line, it is able to hold 4 different groups. Earlier, it was holding the same group, but by going wider, it was simply increasing spatial locality. But now you have a variety. So you can have spatial locality here and here and here and here. You can multiply that factor by a 4 now. So that's how you reduce the miss rate, right? That's how you are reducing the cache misses. Because you're not just leveraging it for here, you're here and here and here. So you're having 4 different groups mapped to the same cache line. So flexibility, which is sort of leading to variety, like you said. So there is less wasted space. I wouldn't say wasted space. I would say it's a more efficient use of the space. All right, so once the valid bit is 1 and something the tags have matched with the address that you generated and the tag field in the cache, one of these guys is going to give you a 1. Once you get that, where is the data? Well, to select the data, you have 4 options, right? The data could be from here, or from here, or from here, or from here. So it's a 4:1 mux. But that 4:1 mux, how many select lines do you need to select 1 out of 4? You need 2, right? In a traditional mux, you need 2 select lines to select 1 out of 4. However, this mux is slightly different because I'm going to use one of these one of these AND gate outputs as the select for the mux. So if this AND gate outputs a 1, then I'm going to select this data. If this AND gate outputs a 1, then I'm going to select this data. And if this AND gate outputs a 1, I'm going to select this data. This AND gate outputs a 1, then I'm going to select this data, right? So I'm using 4 select lines to select 1 out of the 4 options for the data to be read. Different from our conventional mux. In our conventional mux, we only need 32. Can I see that? Sorry, what did I say? In our conventional mux, we only need 2 bits to select. Here we have 4 bits, so slightly different. Why? Because our AND gates to match the tags needed us to have 4 AND gates. So this is 4-way set associative, 32-bit, sorry, I should say 32-bit 4-way set associative cache with 1 word per block. One word per block, which is why we don't need the block offset. All right, next. How many way is good, right? So you go from, if you go to 2-way set associative or 4-way set associative, then you are improving that use of space, right? You have a lot of variety. You have different groups occupying your cache. So your miss rate goes down. But do you stop at 8-way, 16-way? Like, where do you stop? Well, huge improvements are observed until 4-way set associative. After that, it becomes point of diminishing returns. The gain is not that big after 4-way. So you can reasonably stop at 2-way. Beyond that, diminishing returns. Each of these lines is miss rates for cache size. These are all cache sizes, different cache sizes. And it is obvious that if your cache size is small, you will have a miss rate, right? So as you are increasing the cache size, your miss rate will go down. That is sort of obvious. But in terms of number of ways, in all of them, as you are increasing the associativity, you will go down, but up to 4-way set associative in general, you have a lot of gain. All right. The easiest way to do cache-related questions is to have like a rough sketch of your cache. When you're doing a rough sketch of your cache, what are the fields that you're having? Valid bit, yeah, tag, cache index, block offset, byte offset. Byte offset, 2 bits. You can forget about that. It's going to be 2 bits. Then you have a block offset. Purpose of that? Well, to pick out a word from a block, right? So it's a question mark because I don't know how many words I have in my block. If I have 16 words per block, then I need 4 bits to do this. So for block offset would become 4. Beyond that, towards the most significant positions, I'm moving from right to left. I'm moving from least significant to most significant in my address. If I go here, what do I have? Cache index. Question mark. Why question mark? Because I don't know how many lines, right? So it depends on the number of cache lines I have. Tag, number of groups for each cache. Whenever you bring things into the cache, how many different groups can it belong to? That will make up your 32-bit byte address. Okay, I'm going to stop here. Sorry, I went over today. At points, I was slow. Thank you guys for hanging with me. I'll stop recording here.